Good morning, students. Very good morning. Today we have lecture number 6 on electromagnetic induction. Lecture number 6 on electromagnetic induction. So now we will study new concept, self-inductance. Self-inductance or just induction or self-induction. Self-inductance or self-induction. Okay. So let us see what is self-inductance. So self-inductance is the property of a coil. Self-inductance is the property of a coil by virtue of which it opposes the growth or decay of current. Growth or decay of current is opposed. The growth or decay of current through a coil is opposed by a property of the coil, and that property we call it as self-inductance of the coil. So self-inductance of a coil is the property of a coil due to which the growth or decay of current is opposed. The growth or decay of current is opposed by the coil. So it is, so when a current flows through a coil, the increase in the coil is also opposed, or the decrease in the coil. Growth of current means increase in the coil, the increase in the current, and decay of current means decrease in the current flowing through the coil is opposed. That is, self-inductance of a coil is the property of a coil by virtue of which it opposes the growth or decay of current flowing through it. Understood the definition? Okay, so now let us consider a coil. Connected to a battery. And a plug key. So it is a coil. So this coil is connected to a battery and plug key. So now when the plug key is closed, the current in the coil suddenly increases. The current in the coil will increases. When the plug key is closed, the current in the coil increases. This increasing current will cause us, due to this increasing current, the magnetic flux linked with the coil will increases. As a result of this change in magnetic flux, an EMF is induced in the coil. So here, when the plug key is closed, that is, it is made on. Closed means it is on. Open means off. Okay. When the plug key is closed, that is, it is made on, the current flowing through the coil increases. So due to this, the magnetic flux linked with the coil will also increases. As a result of this changing magnetic flux, an EMF is induced in the coil. This induced EMF gives rise to an induced current, and the direction of the induced current, according to the Lenz's law, the direction of the induced current is such that it opposes the increase in the current. The direction of the induced current is such that it opposes the increase in the current. Understood? So thus, the property of the coil which opposes the increase in the current, that property we call it as self-inductance or self-induction of a coil. Understood? Here, so when a plug key is closed, the current flowing through the coil will increases. As a result, the magnetic flux linked with the coil will increases, and an induced EMF is produced. And according to the Lenz's law, the direction of this induced current is such that it opposes the increase in the current. That is, the increase in the current is delayed. That is, the current to reach the maximum value of current, so the current will take a short time, that is the maximum value of current is delayed. The maximum value of current is attained after some time, understood. So that is because of property of the coil, and that property to oppose the growth of current is called as self-inductance, understood. So now if the plug key is opened, if it is opened means off. So if it is opened means off. Now we will off the plug key. It is remove the plug key. So when it is opened or removed, then the current in the coil will start to decrease. The current in the coil will decreases. As a result of that, the magnetic flux linked with the coil will decreases, and induced EMF is an EMF is induced, and induced current will flows. And the direction of this induced current, according to Lenz's law, the direction of this induced current is such that it opposes the decrease in the current flowing through the coil. It opposes the decrease in the current flowing through the coil. So that is, there will be a property for the coil. Because of that property of the coil, it opposes the decrease in the current or decay of current flowing through the coil, and that property we call as self-inductance or self-induction. Self-inductance or self-induction is nothing but you can say it as electromagnetic induction only. That is, so self-inductance of a coil is defined as the EMF induced in a coil due to the change in flow of current flowing through it. That's also you can define. Okay. So did you understood the concept of self-inductance or self-induction? Okay. So now the self-inductance, now let us understand the self-inductance some more. Let I be the current flowing through the coil. Let I be the current flowing through the coil. Then magnetic flux linked with the coil. The magnetic flux link, it is found that the magnetic flux linked with the coil is directly proportional to the strength of current. Let I be the current flowing through the coil. Let I be the current flowing through the coil. Then it is found that the magnetic flux linked with the coil, is directly proportional to the strength of current. Hence, you can write phi is equal to, remove this directly proportional, is equal to then a constant into I. That L is called as coefficient of self-inductance. It is called as coefficient of self-inductance. Self-inductance, or just simply it is called as self-inductance, or simply it is called as self-inductance, or just it is called as self-inductance. So L is proportionality constant. And that proportionality constant is called as coefficient of self-inductance or just self-inductance. So now, if current in the coil is equal to 1 ampere, if the current in the coil is equal to 1 ampere, then phi will be equal to L, or L is equal to phi. That is coefficient of self-inductance of a coil. Coefficient of self-inductance of a coil is numerically equal to the magnetic flux linked with the coil. The coefficient of self-inductance of a coil is numerically equal to the magnetic flux linked with the coil when unit current flows through it. So here another definition I am telling for coefficient of self-inductance or just for self-inductance. The coefficient of self-inductance of a coil. The coefficient of self-inductance of a coil is numerically equal to the magnetic flux linked with the coil. The coefficient of self-inductance of a coil is numerically equal to the magnetic flux linked with the coil when unit current flows through it. Understood? Or self-inductance of a coil is numerically equal to the magnetic flux linked with the coil when a unit current, when 1 ampere of current flows through the coil. Understood? So this is another definition. And now one more definition, one more concept we can tell. So from Faraday's laws of electromagnetic induction. from Faraday's laws of electromagnetic induction. So we know the Faraday's law of electromagnetic induction. The induced EMF is given by E is equal to minus L, E is equal to d phi by dt. E is equal to minus d phi by dt. d phi by dt. Right. Now since phi is equal to, just now we got phi is equal to L into I. This is the formula. Since phi is equal to L into I, so therefore E is equal to minus d by dt of L into I. And L is nothing but a property of the coil, that is self-inductance of the coil, and it will remain a constant. So therefore E is equal to L minus L di by dt, minus L di by dt. Understood? So this is a one expression you can tell for induced EMF. Induced EMF is equal to minus L di by dt. Di by dt is nothing but rate of change of current, and negative sign means rate of decrease of current, you can tell. Okay, if rate of change of current, that is di by dt, is equal to 1 ampere per second. If rate of change of current is 1 ampere per second, then E will be equal to L, or L is equal to E. That is another definition. Another definition we can make: the coefficient of self-inductance of a coil is numerically equal to the induced EMF. The coefficient of self-inductance of a coil is numerically equal to the induced EMF when rate of change of current is unity. When a rate of change of current is unity, when the rate of change of current is unity. Once again, the self-inductance of a coil is numerically equal to the induced EMF. The self-inductance of a coil is numerically equal to the induced EMF when the current through the coil decreases at the rate of unit. When the current through the coil decreases at the rate of 1 ampere per second. Understood? Like this also you can define. Self-inductance of a coil is numerically equal to the EMF induced in the coil when current through the coil decreases at the rate of 1 ampere per second. Understood? So like this. Or coefficient of self-inductance of a coil is numerically equal to the induced EMF when the rate of change of current is unity. When the rate of change of current is unity. So understood? So these all are different ways of explaining coefficient of self-inductance. So from these formulas we got the expression for L. And L is nothing but self-inductance or coefficient of self-inductance. It is L is equal to phi divided by I, and another formula is L is equal to minus E divided by di by dt, that is E divided by di by dt. So this is the expression for self-inductance. Understood? So now the SI unit of self-inductance is, the SI unit of self-inductance is Henry. The SI unit of self-inductance is Henry, and it is denoted by capital H, denoted by capital H. So it is named after the scientist Joseph Henry, who discovered electromagnetic induction independently. Joseph Henry, that is in the beginning we have studied the experiments. So Joseph Henry has discovered electromagnetic induction, and in the name of that scientist, the unit of self-inductance is named as Henry. Understood? So that is L is equal to phi divided by I. L is equal to phi divided by I. So 1 Henry is equal to phi. That is magnetic flux 1 Weber divided by 1 ampere. So that is 1 Henry is equal to 1 Weber per ampere. 1 Henry is equal to 1 Weber per ampere. Like this. Or another way you can give the another one. Or E is equal to that is L is equal to E divided by di by dt. L is equal to E divided by di by dt. So that is L is equal to E. E is in volt. So that is 1 Henry, 1 volt di by dt, that is 1 ampere per second. So when it is taken to the numerator, 1 volt per ampere second. When it goes to numerator, a becomes a to the power minus 1 and s to the power minus 1 become s to the power plus 1. So therefore 1 Henry is equal to 1 volt per ampere second. 1 volt per ampere second. Understood? So now define 1 Henry. Define 1 Henry. So that is self-inductance of a coil is said to be 1 Henry. The self-inductance of a coil is said to be 1 Henry. I will define from there. So that is L is equal to minus E di by dt. Right? Okay. From here we shall try to remove. That is 1 volt. That is when E is equal to 1 volt and di by dt is equal to 1 ampere per second. Understood? So it is the self-inductance of a coil is said to be 1 Henry if 1 volt of EMF is induced in the coil. If 1 volt of EMF is induced in the coil due to the change of current at the rate of 1 ampere per second. The self-inductance of a coil is said to be 1 Henry. The self-inductance of I am defining 1 Henry. Define unit Henry. The self-inductance of a coil is said to be 1 Henry when an EMF of 1 volt is induced in the coil due to the change of current, due to the rate of change of current 1 ampere per second. Understood? It is due to the change of current, that is 1 ampere per second. If 1 volt of EMF is induced in the coil, then the self-inductance of that coil will be 1 Henry. Understood? Okay, this is how we can define units. Okay, understood? So the self-inductance of a coil or self-induction, so both are same, self-induction or self-inductance. Understood? Okay. So the SI unit of self-inductance is Henry and smaller units of self-inductance is millihenry. Millihenry means 10 to the power minus 3 Henry or 1 microhenry. 1 microhenry, it is 10 to the power minus 6 Henry. So like this, these all are the smaller units of self-inductance. Understood? Okay. So now self-inductor. Self-inductor, it is an electric component. Self-inductor. A tightly wound coil of insulated wires. It is an electrical component like a tightly wound coil of insulated wires which opposes the change in current. A self-inductor is a electrical component like a tightly wound coil of insulated wire. A tightly wound coil of insulated wire which opposes the growth or decay of current through it is called self-inductor. A tightly wound coil of insulated wire. A tightly wound coil of insulated wire which opposes the growth or decay of current through it is called an self-inductor. Self-inductor is a device, an electrical component, and this electrical component is made by wounding the wire, insulated wire on a by wounding the insulated wire. So that insulated wire which has been wounded, that wound coil, that is for example a wire is there, a straight wire is there, it is not a self-inductor. It is not a self-inductor when this straight wire is wound in the form of a coil. It is wound in the form of a coil, then it is called as a inductor. It is called as a inductor. A tightly wound coil of insulated wire which opposes the growth or decay of current through it is called a self-inductor. Understood? Okay. So now let us find self-induction of a solenoid. Let us find the self-induction of a solenoid. Okay. Self-inductance of a solenoid. Okay, in the previous chapters we have studied about the solenoid. I hope you have studied about the solenoid. So I will not repeat about the solenoid. I will directly obtain the expression for self-inductance of a solenoid. So consider a solenoid, air cored solenoid. Consider a air cored solenoid. Consider a air core solenoid of length L, and area of cross section A. Consider a air core solenoid of length L, area of cross section A, and number of turns per unit length as N, and N be the number of turns per unit length. Consider a air core solenoid of length L, area of cross section A, and number of turns per unit length as N. That is a solenoid is a tightly wound coil. So like this, and L be the length of the coil. And a cross-sectional area is N, A, and N is the number of turns per unit length. Let I be the current flowing through the solenoid. Let I be the current flowing through the solenoid. Let us consider a air cored solenoid of length L and cross-sectional area A, and number of turns per unit length as N. Let I be the current flowing through the solenoid. Then the magnetic field inside the solenoid, we know that the magnetic field inside the solenoid will remain uniform. The magnetic field well within the solenoid will remain uniform, and it is given by the magnetic field inside the solenoid is given by B is equal to mu naught Ni. Do you know this formula? The magnetic field inside the solenoid will remain constant, and it is given by B is equal to mu naught Ni. Now the total number of turns of solenoid, that is capital N is equal to N into L, whereas small n is the number of turns per unit length. So therefore the total number of turns of solenoid is equal to, that is capital N, that will be equal to N into L. The magnetic flux linked with each turn, of solenoid. The magnetic flux linked with each turn of solenoid is given by magnetic field into A, that is phi is equal to BA. The magnetic flux linked with each turn of solenoid, that is equal to B into A. So B is a magnetic field, that is mu naught Ni and A. So this is the magnetic flux linked with each turn of solenoid. So therefore total magnetic flux linked with whole solenoid, that is entire solenoid, is given by, it is the total magnetic flux linked with whole solenoid is given by, it is equal to magnetic flux linked with each turn into number of turns. Magnetic flux linked with each turn of solenoid into number of turns. That will give the total magnetic flux linked with the whole solenoid. Understood? Total magnetic flux linked with the whole solenoid is equal to magnetic flux linked with each turn of solenoid multiplied by total number of turns of solenoid. That is, the magnetic flux linked with each turn of the solenoid is given by mu naught N I A, and the total number of turns in the solenoid is given by N into L. So therefore total magnetic flux linked with the whole solenoid, it is the total magnetic flux linked with the entire solenoid is given by mu naught N square mu naught n square into I A L. So this is the formula for magnetic flux linked with the whole solenoid. So now, since the magnetic flux linked with the whole solenoid can be done as phi is equal to L into I. Phi is equal to L into I. That is, magnetic flux is directly proportional to the strength of current. Magnetic flux is directly proportional to the strength of current. So it is equal to the constant, that is L into I, and this L is nothing but self-inductance of the solenoid. So therefore, substitute this one here. So that is, substitute, call this as equation number 2 and call this as equation number 1. Substitute equation 2 in 1. So that is, instead of phi, write it as Li. So Li is equal to mu naught n square I A L. So now I will cancel. So L is equal to mu naught n square into A L. So this is the expression for self-inductance of a solenoid. The self-inductance of a solenoid is given by L is equal to mu naught n square A L. And since this n is equal to, that is small n is equal to, that is number of turns per unit length, that is nothing but total number of turns divided by length of the solenoid. Total number of turns divided by length of the solenoid. So therefore you can write L is equal to mu naught n square A divided by L. So this is the final expression. So this is the expression for self-inductance of a solenoid. So the self-inductance of a solenoid is air cored solenoid is given by L is equal to mu naught n square A divided by L. Understood? And this is for a air cored solenoid. If the solenoid is wound on a magnetic material, this is for a air cored solenoid. If the solenoid is wound, that is, wire is wound on a magnetic material. So let us consider that there is a magnetic material of magnetic permeability mu naught. So I will draw another diagram. So there is a magnetic material. On this magnetic material, the wire is wound. So that is like this. Okay. So I is the current flowing, and this is also solenoid. It is also solenoid, but it is not a air cored solenoid, a magnetic material. So the wire is wound on a magnetic material. The permeability of this magnetic material is mu r. Then the self inductance of the coil is given by, that is L dash. I will write it as L dash. So if instead of air cored solenoid, if the solenoid is wound on a magnetic material of permeability mu r, then self inductance of that solenoid is given by L dash is equal to mu naught into mu r, mu naught into mu r, mu naught into mu r, n square A divided by L. So n square A divided by L. So this is the expression for self-inductance of a magnetic material cored solenoid. That is a material cored solenoid, any other material, not air cored solenoid, a magnetic material cored solenoid, where mu r is relative permeability of that material. Thus you can write L dash is equal to mu r into L. L dash is equal to mu r into L. L dash is self-inductance of the magnetic material cored solenoid or material cored solenoid. L dash is the self-inductance of the material cored solenoid, and L is the self-inductance of the air cored solenoid, and mu r is the relative permeability of that material. Understood? Okay. So this is about self-inductance of a solenoid. So now tell me, what are the factors on which self-inductance of a coil depends? What are the factors on which self-inductance of a coil depends? The self-inductance of a coil depends upon the geometry of the coil. that is shape and size of the coil. The self-inductance of a coil depends upon the geometry of the coil and as well as permeability of the coil. The self-inductance of a coil depends upon the geometry of the coil as well as permeability of the coil, or you can tell the self-inductance of a coil depends upon the number of turns in the coil. The self-inductance of a coil depends upon the number of turns in the coil, total number of turns in the coil. And self-inductance of a coil is directly proportional to, that is depends upon the cross-sectional area of the coil. The self-inductance of a coil depends upon the cross-sectional area of the coil. The self-inductance of a coil depends upon the number of turns of the coil, and self-inductance of a coil depends upon the length of the coil. Understood? So what are the factors on which self-inductance of a coil depends? So self-inductance of a coil depends upon the total number of turns on the solenoid, so not coil, solenoid. What are the factors on which self-inductance of a solenoid depends? Self-inductance of a solenoid depends upon the total number of turns wound on the solenoid and cross-sectional area of coils and length of the coil, and also permeability of the material medium. So these all are the factors on which self-inductance of a solenoid depends. Understood? So like resistor and capacitor. See here, resistor and capacitor, these two are also self-inductor, resistor, capacitor. These three components are very important. See here, the self-inductance, that is self-inductance depends upon the geometry. Similarly, resistance also depends upon the length and cross-sectional area. Yes or no? And also capacitance. The capacitor also depends upon the area of each plate and separation between the two plates. Did you remember these things? Resistance and capacitor. So, self-inductance, resistance and capacitor, all the three are of same nature. Same nature means in the sense you can these three components and as well as a diode, and these four components are called as passive components of electrical circuit, or you can say it as ABCD of electrical engineering, which are so inductance, resistor, capacitor and diode. Diode will come in the last chapter, okay, semiconductor diode. So these all are okay, so whatever, okay. So did you understood this self-inductance of a solenoid? Okay. So next, when the solenoid is connected in series. So I will not derive this one, it is very simple, just I will tell it in a direct, okay. Grouping of solenoid or grouping of coil, that is inductor, grouping of inductor, not solenoid, grouping of self-inductor, okay. So if there is a self-inductor, let us consider two self-inductors of self-inductance L1 and L2 connected in series. Let us consider two self-inductors of self-inductance L1 and L2 connected in a series. Then the effective self-inductance of these two, I will tell directly the formula, this derivation is not required. So if you want, if you are interested, you can study from some books available in the library, and many of the books are there, they will explain how to derive this one, a very simple 2 or 3 steps process. So I will just directly write it, that is self-inductance, that is the effective self-inductance in series combination is given by Ls is equal to L1 plus L2. When two inductors are connected in series, the effective self-inductance of that two inductors is given by Ls is equal to L1 plus L2. So now, if two inductors or if two coils of inductance L1 and L2 are connected in parallel, if two coils of inductance L1 and L2 are connected in parallel, then the effective self-inductance is given by, that is 1 by Lp is equal to 1 by L1 plus 1 by L2, or Lp is equal to L1 L2 divided by L1 plus L2. So this is grouping of inductor. So when the two inductors are connected in series, the effective self-inductance is given by Ls is equal to L1 plus L2. When the two inductors are connected in parallel, the effective self-inductance is given by 1 by L is equal to 1 by L1 plus 1 by L2. Understood? Okay. That is not required. This derivation will not be asked in the exam. That's why I did not did it. Only I told you the formula, because that formula will be used sometimes while solving the numericals or somewhere else. So that's why I told about that formula. Okay. So now the next concept is the energy stored in a inductor. Let us derive an expression for energy stored in a self-inductor. Energy stored in a inductor. Expression for energy stored in an inductor. Important for exam, 3 marks they will ask. This derivation they will ask in the exam for 3 marks. Okay. Energy stored in an inductor. Let us consider a inductor of self-inductance L. Let us consider a inductor of self-inductance L. So connected across a battery. Okay. Let us consider a self-inductor of inductance L connected across a battery. Okay. Connected across a battery. Okay. Okay. So let us consider a self-inductor of inductance L connected across a battery. So when a current I through the inductor changes, when a current I flowing through the inductor changes, an EMF is induced in the coil, and the induced EMF is given by E is equal to minus L di by dt. When a current I flowing through the inductor changes, and EMF is induced in the coil, and the induced EMF is given by E is equal to minus L di by dt, and negative sign shows that the passage of current is opposed in an inductor. The negative sign shows that the passage of current is opposed in an inductor. That is, for the current to drive in the inductor, an external work has to be done, an external energy has to be supplied. For the current to drive through the inductor, an external work has to be done, and that external work is done by the EMF of the battery. That external work is done by the EMF of the battery, and EMF of the battery, let E be the EMF of the battery, and it is given by E is equal to L di by dt. The EMF of the battery is given by E is equal to L di by dt. Here, due to the induced EMF, the passage of current through the inductor is opposed. The negative sign shows that the passage of current through the inductor is opposed due to the induced EMF. Thus, for the current to drive through the inductor, for a current to drive through the inductor, an external work has to be done. That is, an external energy has to be supplied, and that external energy is supplied by the EMF of the battery, and the EMF of the battery is given by E is equal to L di by dt. E is equal to L di by dt. So now let a small charge dq is driven through the inductor. To drive a small charge dq through the inductor, the small amount of work done, the small work done to drive a small charge dq through the inductor is given by dw is equal to E into dq. dw is equal to E into dq. That is, the work done by the EMF of the battery. A small amount of work has to be done by the EMF of the battery for a small charge dq to pass through the inductor. For a small charge dq to pass through the inductor, a small amount of work is done by the EMF of the battery, and that work done is given by dw is equal to E into dq. E is EMF of the battery, and dq is the small amount of charge which has to be passed through the inductor, and thus you can write dW is equal to E. E is nothing but L di by dt into dq, or you can write dW is equal to L di into dq by dt. And since dq by dt is nothing but I, dq by dt is nothing but I, so therefore dW is equal to Li di. So this is the small amount of work done for a small charge dq to pass through the inductor, and this work is done by the EMF of the battery. So now to maintain maximum current, through the inductor, the total amount of work has to be done. The total work done to maintain the maximum current, I0 in the inductor, the total work has to be done. The total work done to maintain the maximum current I0 in the inductor is given by W is equal to integration of dW from 0 to I0, that is W is equal to integration of dW, and dW is nothing but this one, that is Li di, and L is a constant, taken it outside, L integration of I di from 0 to I0. So thus after integration you will get L. So integration of I becomes I square by 2 with the limits 0 to I0, and now substitute the limits, first upper limit minus lower limit. So after substituting the limits you will get finally the work done is equal to 1 by 2 L I0 square. Work done is equal to 1 by 2 L I0 square. So this work done in increasing the current flowing through the inductor, is stored as the potential energy. This work done in increasing the current flowing through the inductor is stored as the potential energy of inductor, that is W is equal to U. So therefore U is equal to 1 by 2 L I0 square. So this is the expression for potential energy stored in an inductor, that is energy stored in an inductor. The energy stored in an inductor is given by U is equal to 1 by 2 L I0 square. Understood? This work done in increasing the current flowing through the inductor is stored as the potential energy of the inductor. Thus, that is W is equal to U, that is potential energy of the inductor. So thus potential energy stored in the inductor is given by 1 by 2 L I0 square, and this energy is stored in a magnetic field of the inductor. This energy, where this energy is stored? It is stored in the magnetic field of inductor. This energy is stored in the magnetic field of the inductor. Remember that. The energy stored in a inductor is in the form of potential energy, and it is stored in the magnetic field of the inductor. Like capacitor. In the capacitor also we have derived the energy stored in a capacitor. And where that energy is stored? Do you remember? Anybody? Where that energy is stored in a capacitor? Okay, if you remember, then nice and good. I will not tell. So you only try to recall the things. Okay. So now let us find the energy stored per unit volume. This much is enough. So just for extra, the energy stored per unit volume. That is the energy density. Not energy density. Let us find energy stored in an solenoid. Energy stored in an solenoid. So that is the potential energy stored in a solenoid is given by, that is magnetic energy. What type of energy is stored in a solenoid? Magnetic energy stored in a solenoid is given by Um is equal to 1 by 2 L I0 square. So for a solenoid, For a solenoid, we know that B is equal to mu naught n I naught. B is equal to mu naught n I naught. So therefore, I naught is equal to B divided by mu naught into n. And also we know that self-inductance of a solenoid, just now we have derived. Before this, we have derived the self-inductance of a solenoid. The self-inductance of a solenoid is given by L is equal to mu naught n square I A L. Mu naught n square I A L. This was the expression for self-inductance of a solenoid. The self-inductance of a solenoid is given by L is equal, not I. Mu naught n square A L. Mu naught n square A L. This is the expression for self-inductance of a solenoid. Now substitute these two values. Substitute these two values in this equation. So therefore, UM is equal to 1 by 2. L means mu naught n square A L into I naught. I naught means B divided by mu naught n whole square. I naught square, so this one square. So therefore, UM is equal to 1 by 2. Mu naught square. So that is 1 by 2 mu naught. Mu naught will remain. So 1 mu naught will remain. And this is B square. B square. And n square will cancel. So B square, A square, B square, A square into L square. And A square, L square, B square, A L. Only B has to be squared, not A L. B square A L divided by 2 mu naught. That is B square A L. So B square A L divided by 2 mu naught. This is the magnetic energy stored in a solenoid. The magnetic energy stored in a solenoid is given by U is equal to B square A L divided by 2 mu naught, where B is the magnetic field inside the solenoid, A is cross-sectional area of the solenoid, L is the length of the solenoid, and mu naught is permeability of the air-cored solenoid. Okay. So now the magnetic energy density, that is the energy density. Let us find energy density, that is the magnetic energy stored per unit volume. The energy stored per unit volume of solenoid. The magnetic energy stored per unit volume in a solenoid. Understood? It is called as magnetic energy density. The magnetic energy density, I will denote it as UM bar. So UM bar is equal to UM divided by volume. UM, that is magnetic energy stored divided by volume. Magnetic energy stored per unit volume is called as magnetic energy density stored in a solenoid. So that is UM bar is equal to, it is B square AL divided by 2 mu naught into volume. And volume can be written as volume of solenoid, that is volume can be written as A into L. Volume is equal to A into L, length into cross-sectional area. So therefore, UM bar is equal to 1 by 2 mu naught, 1 by 2 mu naught, that is B square divided by 2 mu naught, B square divided by 2 mu naught. This is the expression for magnetic energy density of a solenoid. Magnetic energy density stored in a solenoid, that is magnetic energy stored per unit volume of a solenoid is given by B square divided by 2 mu naught. Now let us compare this with the electrical energy stored per unit volume in a capacitor. The electrical energy stored per unit volume in a capacitor, we know that. Similarly, I only did capacitor. Energy stored in a capacitor, we have did the derivation, and then after that the energy stored per unit volume. The electrical energy stored per unit volume in a capacitor, we have did. So what is the formula for electrical energy stored in a capacitor per unit volume? That is, I will write it as UE. That is electrical energy stored in a capacitor per unit volume is equal to 1 by 2 epsilon naught, 1 by 2 epsilon naught into E square. So this is the formula for energy density of a capacitor. Now compare these two formulas. This is electrical energy density stored in a capacitor. This is magnetic energy density stored in a inductor. Now compare both the formula. What do you observe? These things are constant. This is constant and this is also constant. So that is, we observe that the magnetic energy density of an inductor is directly proportional to the square of the magnetic field, as like electrical energy density of a capacitor, is also proportional to the square of the electric field. Understood? So both are comes out to be similar. Understood? So it is magnetic energy density and this is electrical energy density. Electrical energy density stored in a capacitor. This is for a capacitor and this is for a inductor. Inductor will store the magnetic energy, and solenoid, this is for solenoid. A solenoid will store the magnetic energy, whereas a capacitor will store the electrical energy. Understood? Hope you understood this concepts. So this much is enough for this class. In the next class we will study about the next concepts. Understood?